Sorry, and so with no further ado, let's flip back to our notes here, and we will get back into vector spaces. So let me just give some context while we're here. So vector spaces, and sorry, I think I moved the spotlight there. Spotlight. Nope, actually I replaced spotlight. Sorry, I haven't done this much. There we go. All right. So where is it going with this? Vector spaces, right? We've seen vector spaces already now for a couple of days. The idea is, what have we seen with real numbers? What kind of patterns have we seen with how we manipulate vectors of real numbers, 2 and 3D vectors and 5 and 10-dimensional vectors and functions? They have surprising amounts in common, but one of the base elements that we can use reliably are these operations of plus and scalar multiplication by reals. So we can add 2 real numbers and get a real number. We can add 2 functions and get a new function. We can add 2 vectors and get a vector of the same type. We can also scalar multiply elements of each one of those kinds of sets and get another one of those elements again back. So there's this commonality that we can identify, and then the mathematical question that we investigate as well, if I can do that with those sets, can I do that with other sets and other definitions of addition and scalar multiplication, as long as those addition and scalar multiplication follow some kinds of rules? And that's where we got the axioms for the vector spaces, this whole big long list here. So what we're going to do today is get through some of the counterexamples. I'll just pause here when we had our little table of examples that work, examples that didn't work. Vector spaces, like I mentioned, the sort of things that you naively work with without thinking about too much. Reals, real vectors, continuous, infinitely differentiable functions, polynomials. And we found a new one last class, which was the set of points along the line y plus x equals 0, x plus y equals 0. That worked perfectly. We also added our new set, W2, with the new, I'm going to put it in quotes here, plus and scalar multiplication. That was our so-called weird vector set, which only included points in this quadrant for x and y, but it had the sort of multiplication when we said we were adding. What we'd actually do is multiply components, and when we said we were doing scalar multiplication, we were using the scalar as an exponent for each component. So that this is a pretty wide variety of things that we can define sensible plus and scalar multiplication operations on. Well, we found that even in R2, though, we could define some subsets where regular addition would not work anymore. For example, a line that didn't go through the origin like this, and that broke down over a bunch of different points, like the 0 vector wasn't in there. We wouldn't be able to do inverses and stuff like that. So there's some interesting relationships even just between different sets that work or don't work as vector spaces. And again, our job mostly with vector spaces is to kind of get an idea of where this boundary line is and what kind of functions are vector spaces, because then we're going to learn about a bunch of properties today that apply to all vector spaces that we can just pull out when we need them. If we're unlucky enough to encounter something that's not a vector space, like, now I got to do a whole pile of work figuring out what the rules of this world are. We tend to try to work in vector spaces. And fortunately, this is a pretty broad category, so we get to use it a lot. All right. So we left off after the weird vector space here. There we go. All right. And the idea for today is to do some proofs. That'll be the last bit we're doing, but also just another take on why are we forcing you to do linear algebra? And one of the perspectives, besides that rule idea of understanding what rules apply if you're in a vector space or not, the extra element, helpful element, can be mapping what you do understand about vector addition. I know for some of you that was sort of new even in the fall of this term, but hopefully you've gotten a good feel for it now between calculus and physics and all the practice you've gotten there. But imagine you're in 2D space here, and you have a u vector, and you have a v vector. Actually, let me do 2 different colors. Oops. There we go. Nope, it's wrong. There we go. So we have our v vector here. And we say, well, how do I do addition? Well, the head to tail addition is what we learn first. We put the v tail on the end of the u head, and we add them together. And then that new vector is going to be u plus v. But as soon as we do that and we have this picture, then we also get for free, really, the commutativity. Commutativity, which again, remember, means just that you can swap the order of addition. So I can get to this endpoint by going u then v, or I can get to that endpoint with v plus u. Doesn't really matter. And that means mathematically we can replace one with the other. And so that gives us those kinds of rules that we can sometimes work with where it's helpful. The other thing is we can build algebraic things out of this. We just do this calculation and we can express it. We can use commutativity, it's a hard word to say, commutativity on these kinds of expressions when we're just working with algebra without a picture necessarily that goes with it. So functions like if I define a function h as being f plus g, I can guarantee that that's also equal to g plus f if that is something that would help me when I'm trying to analyze something, a particular scenario. The other thing that's probably more interesting for us is if you imagine, let's do an R2 here, because that's easier. So R2, imagine any vector at all, long, short, down this way, down that way. You know that we can get to any of those vectors by adding up just two pieces, combinations of two pieces. So the sometimes called the I vector, or the I with a little vector hat on it, J hat, or the J vector. Any vector V, which is in R2, can be written, as sum A times the I vector plus sum B times the J vector, and V equals, where A and B are in the reals for sum. Okay. So hold on, wait a minute. This is something you probably have not thought of, but it kind of makes sense, right? I can get to any point by going out in the x-axis by a certain amount and then up the y-axis direction by a certain amount. But if you take a careful look at what you're doing with this, you are doing scalar multiplication and you are doing addition of vectors. So this construction here is everything that goes on in vector spaces, vector addition and scalar multiplication. And so when you get to the kinds of constructions in function spaces or any other set that has a plus and minus, oh, sorry, transcription should be on. Any other vector space that you can identify, then you can guarantee that, as we're going to find out shortly, there's going to be some rules around this, but you can define any vector V as equal to the linear combination is what we're going to look at here. Combination of some building block set, some small, generally small, I'm going to say small, in quotes, set of building blocks. I like to say building block vectors. So here, the building blocks for all of R2 in some sense to are just the I vector and the J vector. There. By some definition, if I have the I and the J vector, I can get everywhere. I can build any vector in this set here. And the same thing is kind of true in polynomials, if you think about it for a second. In P2, what are the building blocks of polynomials of degree 2? Or that's what that is, polynomials degree 2 or less. 2 or less. Then really you just need constant functions, x's and x squareds. If you have those values, then you're good to go. if you have those functions, you can build any polynomial you want through this kind of scalar multiplication and vector addition here, but vectors are functions here. So by adding functions and scaling them by real values, you can build all the polynomials. So that's the kind of translation where we have something that's conceptually true in R2 that we kind of get, and we can draw pictures and understand it that way, versus things that are a little harder to draw, but we can figure it, because addition works the same way, because scalar multiplication works the same way, we're going to be able to make very powerful statements about these other things that satisfy the vector space rules. So leave that there. Okay. One of the things I think that's going to, one of the things that's going to be crucial in the assessments in this course, we're going to have procedural computational type questions, and we're also going to have proof questions. You've already seen some of those in the web work for week 1. I think one of the tutorial problems as well had a lot of set stuff in it. So what I wanted to do here is spend some time doing some proofs that sort of illustrate how proofs are built in these kinds of contexts. All right. So the kinds of proofs we're going to be looking at here are things that relate to the vector space axioms. And remember that we say this combination of a set, the addition operator and scalar multiplication, we only call that group a vector space if it satisfies the axioms. So if we say this is a vector space, we can guarantee that all the rules for the vector space axioms apply. The nice thing is, though, is there's a bunch of secondary properties. So if the axioms are all true, then we can also conclude a bunch of other things every single time for every single vector space. And that's handy to have. The axioms are kind of the distilled essence of a vector space. But once we have that, we can spread that out to a bunch of other things that are also true. And that's really how a lot of math works these days. We've got a sort of core set of axioms is where we start, and then we try to see what else we can prove based on those. So let's see this as an example. In the vector space V, we say we've got that rule about zero vectors, and actually I'm going to do that here with a quick clicker question. There we go. So we're going to flip over to clicker for a second, and then we're going to talk about the zero vector in more detail. Let me just get that clicker question up. Either way. There we go. Next question. There we go. Yeah, so actually we'll put it right over here. So in a vector space, what makes the zero element or the zero vector special? Like, we give it the special status, we give it the special label. What is that label? Or why is that label there? And I think you guys probably see it in your own things better. There were zero vectors in these things. I swear to God, they were there.
It doesn't show up on my
computer. No. Really? Well, that is so annoying. I went through a whole pile of frustration getting those formatted nicely to look like these guys. Well, that's going to be less helpful if you can't read the whole sentence. So, all right, we won't belabor this though. So if the zero vector doesn't have an added inverse, if you add 0 to any vector, you get the 0. Oh yeah, this makes no sense because these guys look identical. All right, I will work on that for next time. I don't know why it showed it in the preview, but not here. All right, so the answer is, if you have a zero vector, it's an additive thing. So if I take any u vector in our set V, then u plus the zero vector has to equal the same vector again. No change after addition. No change after adding 0. And again, this makes sense in a vector. If you have the vector 1, 2, and you add the 0 vector to it, you get the 1, 2 vector back. If it's functions, if you take a function, then you add the constantly 0 function to it, you get the same function back. It's kind of a sort of a null operator. One of the questions that comes up, though, is maybe there's more than 1, 0. Maybe we need to broaden our imagination again, like we did with the weird vector space. What if there's more than 1 0 vector? Is that possible? So here's where we can use the axioms and do some steps out from the axioms and prove that no, actually the there is only one zero vector. There has to be a zero vector to be a vector space. And if you have that zero vector, there's only one of them. So, so the weird thing we're going to do here is we're going to assume we have two zero vectors. So our goal is going to be to show that they are actually equal. They must be equal. So this is a classic example of a proof where you imagine what a contrarian would tell you. Like you're saying, there's only one zero vector. That's all there is, one zero vector. Someone else says, I think there's two of them. And you're like, okay, let's go with your hypothesis. Let's say there are two zero vectors. Let's work with those and see what kind of relationship they would have. And so let's give them some names. Give the names, let's call it the zero vector A and the zero vector B are both, actually not even are both satisfy the zero vector conditions. Or axioms for a vector space. So someone says, I think there's two of them. You're like, sure, let's take that and see what happens. So we've got two things that satisfy the axioms. Our goal is going to be to show that both of those zero vectors have to be equal to each other, that they are essentially the same element. And the way we can do that is start with one of the zeros. So let's start with the A1. All right, well, what's the A equal to? What can I replace it with? Well, what we're going to do is we are going to go up to the definition. So this is the classic proof thing of, I've got some construction and I want to use the axiom somehow to rewrite it. So what we're going to do is we're going to treat 0A as our U for a second here. So treat like U in U. I'm just going to flip this around a little bit. So here it's U equals U plus 0. Equals U plus the 0 vector. So it's going to be the same vector A, but I can safely add the other 0 vector to it if I want. So this is saying basically adding B, adding 0B, the second one, doesn't change value. Okay, let me just pause there for a second. So we're taking this equation here, which is how we work with zeros. And for now, we're just using U as our 0A. So if I take my 0A and I add 0, the 0, which is a 0, 0B here, I should get back 0A. Well, then, hold on. If I have this, I'm going to go up to this equation again. Remember, they're both zeros. Now I'm going to flip it around. I'm going to say, well, if I have two things that are added, this time I'm going to call that my U, the thing that I'm adding to, and then I'm going to add the 0 vector to that. So this time, oops, we're not doing that. There. And I'm going to go from here to here. Let's do this in a different color. Treat 0B as the U vector. And we said, well, these are both 0 vectors. So if I add the 0 vector to something else, I get the something else back again. And if you look at that transitivity property, that means that 0A, skip that step, has to equal 0B. So 0A equals 0B. So both zeros are actually the same element. Element of, what was our vector space? Our vector space set was V. So you think there's only one 0 vector. Someone comes along and says, oh no, I think there's two of them. And they both satisfy this rule. And you're like, okay, let's try that. Let's give them names. We start with one of them And then we just apply that rule through different lenses, but we apply that rule twice and we get back to 0b. And so then we get that conclusion that, well, even if you said there's two different ones, they actually are equal to each other. So they're really the same thing under the hood. So that's an example of a proof where we're using the axioms, and it's usually a combination. It's sort of one statement to the next statement, and then there's a rationale for each of those equal signs. Some people like doing it in columns, kind of like a lot of you would have seen this in geometry. That's a perfectly valid way to do it. We don't typically do that as much in algebra, but if it helps keep things organized, it's worthwhile doing.
For that last one, would you have been able to say that 0 is equal to u minus u, and then since they're both equal to that, then they're equal to each other? Or can you not rearrange the axioms like that?
The 0 is sort of defined by this. The inverse is what has u plus minus u equals 0. So it's harder to define 0 that way, because you have to get into the inverses, and we don't really want to complicate it if we don't have to. That's a reasonable argument, but there's probably a way to do that as well, honestly, but this is the more straightforward one. Yeah.
Thank you.
Excellent observation. In fact, we're going to get to the additive inverses right now. So speaking of which, oh no, it's going to look even worse. All right, let me try it. Let me just see if it goes to the next. This one works. Oh, this one sort of works. 3 of the answers are there. All right, so let's try this one. In a vector space, what is the property of the additive inverse? And you can select a few. Perfect. People are honing in on A and D, which is good because they can actually see the check marks, which is unfortunate. But exactly, it doesn't matter the order. You can do U plus the inverse or the inverse plus U, and you get to 0. So this is what you were hinting at before, is the 0 element shows up in another axiom as well. All right. Let's take a look at this uniqueness property again. So you know, in real numbers, if I give you 2 and you want to find the additive inverse, that's going to be -2. And it's minus, there's no minus anything else that's going to be the additive inverse. And the question is, well, is that true in general, that there's only one additive inverse for every element? And the answer, fortunately, is yes. And we're going to prove that here. So we're going to let V be in our set. And again, we think there's just one inverse, but we're going to assume that someone came along and said, oh, I think there's 2 inverses for that V there. So okay, let's take a look at it. And we're going to assume, let's call it, we assume that V has 2 additive inverses. And let's give them a name. So I'm going to put in square brackets here to kind of make it a unit. And same logic as before. Sorry, same logic as before. Get closer to the mic. There we go. All right. Our goal is to use the axioms to show that if we start with one of them through a bunch of chain of logic, we can show that it is equal to the other one. All right. So how can we get there? Well, let's start with one of them. Let's start with negative VA. Now we are going to sneak in that 0 idea. So we're going to add 0 to it. So that is the same as VA plus 0, our 0 vector. And so this is the U equals U plus 0 axiom. All right. Now, why is that helpful? Well, again, the rule we just saw in that question on clicker. Sorry, that question there. How do we know, sorry, what's the rule about these inverses? So the additive inverse is this and this. Let's do this little color change here. We're going to have that V plus VA negative equals 0, and also V plus negative VB equals 0. Why? Because we said these are both additive inverses. So if I add them to this element V, I get 0. And that's true for both of them because we said they're both equally valid additive inverses. And you can see the hint there. Now I have a 0 to play with, and I have a 0 in this equation. So what we can do is start introducing some other values like, hey, VB here. So let's expand this. That's right, I'm square bracket in the wrong spot there. So negative VA is there as a block, and that can be replaced by V minus, sorry, trying to get this right here. V plus our inverse VB here. And this comes from the axiom on additive inverses. This guy here. Okay. Next up, I want to cancel some stuff. Gosh, it'd be really nice if I could get rid of my VA, because I have VA, but I want it to equal, sorry, negative VA. I want it to equal negative VB. Well, I don't need these brackets anymore because addition is associative. I can group them whichever way I like. So I'm going to group it this way, negative VA plus V plus the negative VB. That's the associativity of addition. And then last but not least, this, oh wait, that's the same as this rule, only with commutativity applied. I can do it in either order. So this is equal to the 0 vector plus my inverse labeled B. And that comes from our axiom on additive inverses again. So I should be doing this in red here. Axiom on additive inverses. And then, oh wait, we have 0 plus something. Well, I don't need that 0 anymore. Adding it to something doesn't change it. That is from our 0 axiom. And so, hey, look at that. We started with VA. We did a whole pile of work, exactly like we indicated we would do here. And at the end of the day, we ended up with our negative VB, sorry, negative VA, negative VB. And so this tells us that negative VA would equal negative VB. And so both additive inverses are the same value, are the same. So if anyone comes along today and says, let's make this true, let's come along with 2 different additive inverses, you can show, well, if you do some work, those are going to end up being the same. Sorry, now I have seen some stuff going by in the chat, but I had good flow there. I didn't want to ruin it. I think I had good flow. Let's take a look. All right. So how do you know the proof is overly sufficiently proved? There's definitely some meta stuff there. In this case here, though, if you look at each step, the idea is here's where I started, here's where I ended, and there's nothing more that you can really add in between, and every one of these equalities is dictated or comes directly from one of the axioms. So that's the kind of structure. I don't think you get any simpler than this. There's no steps you could really take out. And I also don't think you can get too much more complicated. Most of the proofs in this course are going to be on this scale, like 1-page-ish kind of things. So it definitely takes some flavor, definitely takes some practice, but away you go. Excellent. So do you have to show this equality as you go? My short answer is for now, yes. It would be a very smart idea for you to put it, like if you put this on a test, no one debates what you understand. No one can debate about what your chain of logic is. If you don't put these reasons in there, then if you make a mistake and make an equality that's not true or that jumps several steps at once, that shows that you're not connecting things in a clear way for a reader. The idea is that a proof should be something that anyone can follow and go, if I know the axioms and I'm looking at your proof, I know exactly why you're getting from how you're getting from step to step to step. There's no ambiguities there. So I think it's a good idea to put those in there, whether it's little arrows or, again, if some people find it easier or more intuitive to page here. So to say negative VA equals negative VA plus 0. Do this in a column, that would be by the 0 addition axiom. And then in the next line say, well, that's equal to negative VA. It's easier to run out of space when you do it this way. What was our next line? It was plus V plus the other inverse VB. So that's the VB is an additive inverse. Additive inverse. So that can be a nice way to structure where you just do it, the chain of logic for equalities here for these kinds of problems, and then state the reason on the other side. That can be really nice. And so, yeah, so the question is, have we debunked the 2 additive inverses? Yes. If someone says, I've got 2 additive inverses, you could walk through this chain and say, well, your 2 additive inverses are equal to each other. They have to be, because every step along the way was just using one of the axioms of a vector space. So if we're in a vector space, those 2 additive inverses are in fact the same thing under the hood. So Elliot has a good question. In fact, we're going to get to that next one, which is what are you allowed to kind of cancel when you get to more complicated equations here? The axioms are really, really basic. It feels weird to use them that way, but they're really, really basic. And so we do things with cancellations that are consequences of the axioms without you realizing it. So let's do an example here. If we have this pair of sums here, most of us would just scratch out the V's and say that U equals W, which is exactly what I think you're saying in the chat there. So the question is, can you always do that with vectors, with real numbers, with functions? The answer is yes, thank goodness. But it's not actually trivial to prove that using just the axioms. So yes, you're going to reinvent the wheel in vector spaces here, but it's incredibly powerful to be able to say, from this small set of rules that we have, we can actually show that all these complicated behaviors that we do when we're solving equations are motivated and come directly from, in a completely rock solid way, from those axioms. So let's take a look at that here. So again, what we're going to do is start with one of these numbers and do a chain of logic and get back to W. And this one I'm going to try doing as a column one just to see or show how it might be done that way. So we're going to start with U. Sorry, vector. All right, so we start with vector U. And pretty much the only thing we have for these kinds of things is the 0 vector. The 0 vector is the only thing we can safely add to these things without breaking stuff down. So U plus the 0 vector. And I'll put my little column here. Get rid of this junk so I have some space. And that's because of the 0 addition axiom. Okay. Now, I really want to get this vector V in here somehow. How can I get the vector V in here? Oh, the 0 vector can be broken down into the V vector plus its inverse, right? Oh, so let's replace that. So that's I keep putting hats on things. There we go. They're all vectors, but I'm just going to put a hat on the U, on the 0 vector just to make it clear. So we have the U already, but then we can split our 0 vector into a positive V and its additive inverse. Okay. So how does that help us? Well, what we're going to do is regroup this. I have an equation for U plus V. So I'm just going to regroup as U plus V. And then I'm still left with the additive inverse left over. And that's from associativity. Oh, wait. U plus V is equal to W plus V. So this is our, I don't want to show it there. I've got a column to do this in. This is going to be something I can replace with W plus V if I like, from the given statement that U plus V equals W plus V. And then we still have that little additive inverse on the tail end. And you can see where this is going, because now we associate back again. If I put these together, oh wait, I'm going to get a 0 vector, and then there we go. So we're going to reassociate W by itself, leave it lonely on the left-hand side there. And then we can look at these two things here together. They're going to give us the 0 vector because they're additive inverses. Axiom for additive inverses. And then we're left with W because of the zero additional axiom. All right. So at the end of the day, if we said, so this one's conditional. The last few were just proving uniqueness. Here we said there's a statement that's also true. So if I have U plus V equals W plus V, if those are the same thing, then we can, I'm going to say it here, we can cancel the V's. U is the same as W. So that's a handy thing to have, because again, you kind of know this already, but and this would get to that other strategy someone put in the chat with the V plus the, anyway, we're not going to go into that because I think we're running a little short on time as always. But this leads us to the conclusion that we can just cancel one of these values on either end, and we'll get the equality of the first two things. Now, a fun characteristic about matrices later on, we're going to have equations that look like this. It's going to be multiplication. So in regular multiplication, if you, sorry, I'll do this. This is an aside, do not copy this down. But if you had, A times B equals C times B, you could just cancel the B's, right? Same thing for multiplication. It turns out with matrices, you're not going to be able to do that. So there's times where you can't just cancel. It actually doesn't work that way. So in all the vector spaces, which are things that you've grown up learning to use, and they all seem to follow the same rules, there's reasons for that. But not everything is going to be like that as you get a little bit further into some of the mathematical models and mathematical structures you'll be using. So just keep your eye open for that. All right. I do want to hit at least a couple of these. These are the ones that are sort of obvious, but also if you look carefully at the axioms, they weren't stated. We had the 0 vector, right? It was a thing, but what's less obvious, but thankfully true, is that you can get the 0 vector in any space, in any vector space. God, my writing's getting worse. I was afraid of that. In any vector space by computing the scalar product 0 dotted with V for any vector V. Any vector V. So what you'd expect is, how do I, 0 times something is 0. That's an important ingredient for a lot of things. But if you think about functions, like if you take 0 times the function, x squared plus 1, you actually get the 0 function back, 0. So I want to be careful here, or clear about this. When you're doing this kind of math, this is a scalar 0. This is a real number, element of the reals, whereas this is the 0 function, the function that's always equal to 0. It has to be because we're talking about multiplying a function by this scalar. So this is like the 0 vector in polynomial space or continuous differentiable space. So it's nice that this is true, but it's not obvious or guaranteed from the axioms. We have to actually figure this out from the axioms. The other relationship that if I take a vector, sorry, if I take a real number and I multiply the 0 vector, then I still get the 0 vector back. That's also true. I think we're going to prove, I'm going to prove this one. I think that's the one that's more interesting. But basically the rules that you kind of know and love, that 0 times something equals 0 is true, but it's true because of the axioms of a vector space. And it's actually more subtle than it might look because of these actually different formats. This 0 is a scalar, this 0 is a vector. It's not clear that this would always be the case, but fortunately it is. All right. So, oh yeah, excellent question. So does that mean we can't use a cancellation property? Now that you've seen these properties, and so they're all the ones that are listed in this handout in this PDF here, the zero vector being unique, the additive inverse being unique, the cancellation property, yes, you can use those. So if some other proof is asking you to do something, you can pull these properties out. If we want you to go through this kind of level of analysis, we will say specifically prove the cancellation property, i.e. given that blah, 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 3 vectors, all that. So if the question is phrased pretty much exactly like it is at the top of this page, you'd have to recreate this proof. If it's something of, one stage further out than this, usually some kind of scenario. So some vector space with this property, show this, you can absolutely use this cancellation property because it's true for any vector space, anywhere, anytime. This is always true because it came directly from the axioms. So it is a bit subtle, and we'll try to make it as clear as possible in any question, kind of what rules apply. Yeah, okay. So where are we here? We're going to prove A. So the idea that the scalar 0 times any vector gives you the 0 vector is, here's one way to prove that. So what we want to do is start on the left-hand side. So this, again, is the typical thing of, if I'm trying to show 2 things are equal, I'm going to start with one, do a bunch of work, and get to the other. So that's the meta strategy you should have in mind. What do I do in proofs? I'm trying to prove this equals this. Well, let's start at one side. And it's usually easier to start with the more complicated side and make it simpler. So we're going to start with there. We're going to start, Control Z, there we go. We're going to start with 0 dotted with V. Vectors. All right. And I want to get down to the end here. I'm going to do a bunch of work, and I want to get to just the 0 vector. Now, this is not, I don't think, that obvious at all. So let's work through this carefully here. Yeah, this one is not, surprisingly not obvious for something that seems obvious. I'm going to do a little expansion here. And I'm also going to clear out some other junk here. Whoops, that's weird. Delete. Still in business. Yeah, okay. Delete that. All right. So why can I do that? Well, 0 plus 0 equals 0 in the reals. This part here is just real numbers, so we can do that. Or if you want the 0 property in the vector space of just the reals, then we can distribute that. So we can get 0v plus 0v is the same thing. So that's distribution. Distribute. All right. So how does that, I need to get the 0 vector in here somewhere, right? So how can we build that in? Well, we can add that to anything we like, right? Sorry, I'm looking at my own notes. I'm having a hard time following my own proof now. I'm looking back at it. Good times, good times. Yes, okay. So what we're going to do is take a little break there so we can relate these 2 things here to each other. And we're then going to add the 0 vector at the start. So we're going to have the 0 vector. Now look at, oh my God, handwriting. Now we're going to consider our 0.v. It's also equal to 0v plus the 0 vector. And that comes from our 0 additive axiom. Okay. Now that doesn't seem very helpful until we equate these 2 things here, 1 and 2. And again, this can feel I imagine for 99% of you, this feels so meta, like, what is happening right now? Why is this so complicated when it just looks so easy? But here it is. We're trying to use the rules we had. If we set 1 equal to 2, what do we have? We have the 0 vector plus the 0 times v. So again, remember, this is a scalar, that's the vector, this is a vector. And we said that's equal to 0 times v plus 0 times v. Well, we just saw that on the last page. U plus v is equal to some other vector plus v. And what was that property that we just, so going back to the question, can we just use that cancellation property? Absolutely, we can just pull it out right now. And because this is the same vector here in both cases, we can just cancel cancellation property. We can just cancel those two outside ones. And what are we left with? The zero vector is what we get when we do zero scalar times any other vector for any vector in V. Any vector V in our set. So the reason we wanted to expand this thing out is so we could turn this expression up here into something that had something extra on it each time. And that extra thing we just could add, basically we could add zeros for free on either side. And at the end, we ended up with this property here. So that is a way, there's a few other ways too, but to prove that if you take any vector and multiply it by the scalar 0, you're going to get the 0 vector. Oh, no, it's not that. It is a sophisticated mental challenge that takes practice. It is not random, but it's the kind of, it's a combination of an art and a skill. But at the end of the day, you have to know the rules that you can play with. What are the rules that you've either started with in the axioms or that you've proven since then, like the cancellation property. And then you're trying to, it's like a jigsaw puzzle. You're trying to put those pieces together. It's more one of those pipe games where you have a start point and end point. You're trying to draw some kind of connection with the pipes that you were given. It's really that kind of problem solving, especially for linear algebra. I'm not going to lie, it's going to take some practice. If you haven't done this with geometry, it's going to be a hard go. People who have done this with geometry and angles, show the opposite angle from this parallel line is something else. You are in much better shape than people who have not done this before. It's learnable, but it's just easier if you've seen this kind of structured proof before. So, all right. I'm just keeping an eye on the time. I don't want to hold anybody late. So, yeah, I will fill in these proofs. That's what I'll do so you can see them, but I won't go through them. They have very much the same flavor. So again, like 0 times a vector gives you the 0 vector. The same thing is true that for the additive inverse. So the additive inverse can be built. You can build the additive inverse, by taking, additive inverse of a specific vector, of any vector V, by computing -1 scalar product with V, -1 real scalar product with V. So everything you've always done. So this is basically what you do in equations where you say, I've got something plus negative V that's equal to negative V, which we also think as -1 times V. Those are all the same thing, only because we're working in vector spaces and we have those properties. All right. So again, I will fill in these proofs here, so you have those available. My last little quick comment is 2 quick comments. These theorems can feel obvious because you're reinventing the wheel. You've been using these things without knowing it all along. Sometimes now we're unpacking the box of things that you already know and saying, why are these true? And pointing out the fact that they all flow from the axioms for vector spaces. As we encounter new vector spaces, having this structured rationale for why these rules are there and what they hinge on in the axioms can be surprisingly helpful. I do want to tie it back just briefly to 171. So that's for raise of hands for your class right now. So who remembers when you're looking at the spring system? I'm guessing a lot of you, because some of you wrote your exam just last Wednesday. So when we looked at the forces, we got this mass times acceleration as a spring force and a damping force. So we're changing gears here. What we ended up with when we were willing to accept complex numbers as being useful, not real, complex numbers existing and being helpful, is that we really quickly got to solutions to this equation, which again describes the motion of this spring mass system, by just using complex numbers and the exponential derivative rules. It was surprisingly like 3 or 4 lines to get here. Then we threw in this one statement: any linear combination of these 2 solutions is also a solution. So we got these 2 things here, and then I threw that out in the class and said, wait till linear algebra, here we go. And that's what we helped with Euler's formula, which was that e to the I bt here is the same as cos bt plus I sine bt. That relationship between the exponentials and cosine sines. And I say, well, if we have this rule, we can make any combination we like out of those. And that comes straight from vector spaces, right? This, again, is a scalar multiplier. Z1 times e to the a plus bit is a scalar, oops, wrong bracket, is a scalar multiple. And if we accept that the space of here continuous functions in the complex numbers is a vector space, then I'm allowed to do this, and I'm going to get another function that I can use. I can also then add some other function because adding functions is safe. And so this is going to be our vector space addition. And so what magic wand I would wave now that you've seen what you've seen is the solutions to a linear equation form a vector space. If you've found two solutions, you're allowed to add them, and you're allowed to do scalar multipliers of them any way you like. And then you'll still have other solutions. You're just going to get more and more solutions. Just like in a vector space like R2, all you need are the two building block vectors here, and then any other combination is also going to be in R2. So that's the kind of logic that we can then pull out and apply to other disciplines and domains. All right, I've held you way too long, so I'm going to make everything else here from here on in optional questions. I'm going to look back to the chat, and otherwise we will see you on Tuesday next week.